I think we can get started. There are still some people filtering in, but they, I think, will find their place during the introduction. As president of the Ocean Sciences section of AGU, I would like to welcome you to this year's Sverdrup lecture. As you know, the Sverdrup lecture is one lecture in a series of the BOWE lecture series, a union lecture series, and the presenter is selected by the Ocean Sciences section. It is a great pleasure for me to introduce today's speaker, the presenter of the Sverdrup lecture, Charlie Eriksen. Charlie is a professor at the School of Oceanography at the University of Washington in Seattle. He told me that he's a native of San Francisco, so a nice place actually to come to give his lecture here. He got his undergraduate degree in 1972 at Harvard with Jim Baker. He then moved on to get his PhD in 1977 from the joint MIT Woods Hole program working with Carl Wunsch. After that, he did a postdoc at Woods Hole with Jim Lloyden. He moved on back to MIT, where he was a faculty member till 1985, and after a short visit at Scripps, he started his present position as a member of the faculty at the University of Washington, Seattle in 1986. Charlie has worked on many topics with many methods. It includes ocean dynamics, internal gravity waves, mixing processes, equatorial dynamics, flow near topography, and regional circulation, focusing on process-oriented studies. Experimentally, he used as his tools moorings and, more recently, starting at around 1995, autonomous platforms, most notably the gliders that he was so instrumental in developing. By now, according to Eric, there are about 150 gliders have been built and are being used, most of them, right now. And there is a transition from having the gliders built mainly at research institutions to making them also commercially available. So Charlie will talk to us today about what these new tools will allow us to do in terms of oceanography. And the title of his lecture is The Autonomous Revolution, Transforming Ocean Observation with Mobile Platforms. Before handing the microphone over to Charlie, I would like to present him with a certificate as this year's Sverdrup lecturer.
Thank you very much, Peter.
Please
Well, thank you, Peter, for a very gracious introduction. It is a lot of fun to be here in San Francisco and give a talk as an aging adult. I grew up around here. I grew up in the peninsula, and I'm only sorry that I didn't achieve this honor in time for my mother and father to be able to listen to me, but I dragged my brother in anyway. You can look around and see if you can find who my brother is. But it really is an honor to speak about this. It has been sometimes it's a lonely business in science, and you don't always feel appreciated. There aren't a lot of pats in the back. Oftentimes you're living from one grant to the next, just trying to survive and keep your research group going. That's what everybody in this room knows about. I'd like to say to the young people that there is light at the end of the tunnel, and hopefully you'll all have long and fun careers. I certainly have had a fun career, and what I chose to talk about today about autonomous vehicles is really the most rewarding part of what I've done in oceanography. I started out being a guy who used moorings, and that's because when I first went to sea, I remember standing under the meter wheel getting wet as the meter wheel in the CTD was dripping. And I thought there really has to be a better way to make temperature and salinity kinds of measurements and current measurements. And so I went to the first kinds of autonomous instrumentation, really moorings, internally recording current meters and the like on moorings, and got frustrated with those at one point because I could never have enough to be able to look at space and time together. Certainly, time series were well recorded by moored devices, but not space. So I really got interested in these autonomous platforms. I'd like to acknowledge thank first the Ocean Sciences section for selecting me and inviting me here. The funding agencies as well, Office of Naval Research and the National Science Foundation have together supported most of my work over the years. I've had some money from NOAA, part of the development money for the Sea Glider project that I'll talk about it later in the talk was from the National Oceanographic Partnership Program, and some of the collaborations I've had have been with people funded by NASA. My primary co-PIs recently have been Craig Lee and Mary Jane Perry, Peter Rhines and Steve Emerson, and in terms of co-workers, particularly Jim Ossie, the design engineer for Sea Glider in my research group, Bill Fredericks, Kirk O'Donnell, Jim Bennett, in earlier years Neil Bogue, Fritz Starr with the Sea Glider Fabrication Center, in earlier years also Russ Light at APL, and many others that I can't name all. And recently my couple of particularly enterprising students, Nick Barrett and Noah Pellin. So here's my outline. I'm going to talk about the challenge of sampling a turbulent ocean and talk about neutrally buoyant floats, and I'm really talking about them mostly as a tourist, as an admirer from afar, and about profiling floats as well. Profiling floats are, if you think about it, they're neutrally buoyant floats that have a little bit of control. They have some time depth control. And the next thing you could do would be to have three-dimensional control as well as in time, or four-dimensional control, and that's what AUVs and gliders do. And at the end of the talk, I'll get to talking about gliders under the ice and also our new 6,000 meter depth deep glider. So I'm going to start with these two very different views of ocean circulation. The piping diagram that we all grew up with, as an old guy, we all grew up with. Students these days probably aren't introduced to this completely as the truth, but when I started oceanography, people were looking really for a mean circulation, trying to define it. And there are theories like this one of Stommel's of the abyssal circulation fed by sources and sinks with flows basically going up. If I can do this, I can't face in this direction and move the pointer like that, up and down by the western boundaries of the ocean, feeding out into gyres in the interior. And it was that sort of picture that it was around in the late 50s. Here's somewhat later is this cartoon of Wally Brokers that a lot of people have a lot of trouble with, as do I. It's very, very schematic, and if that circulation really exists at all, but certainly certain parts of it certainly do exist. And then here's another piping diagram from Bill Schmitz. These things could get more and more complicated. You can find more complicated ones in the literature. But really, the other paradigm for ocean circulation is the eddy flux paradigm. And I just picked out an easy-to-get model. It's on the web for the Naval Oceanographic Office's global NLOM. This is a 1/32nd degree layered model. And the first thing that you look at, this is sea surface height on a particular day. It was last week when I made this slide. There's a lot of puffiness and lots of little eddies all over the place, particularly in the western boundary region. But there are all these eddies all over the place. And if you look at sea surface temperature, it also looks fuzzy. And depending on the color scale, you'd find eddies everywhere. It's not just that the eddies are up here, they're also down here. You just don't see them because the color scale isn't picking them out. So this is the same day, the same model, showing the speed. And in speed, you start to see the eddy character even more. And the two kinds of things that you pick out are lots of motion along the equator, lots of eddy sorts of things, time-varying motion there. Some strips and stripes in the Southern Ocean, some rather strong stripes on western boundaries of strong straight flows. Those are the western boundary currents, and then they end up going off into the interior of the ocean of their respective basins, eddying away and meandering and breaking up into eddies. And if we go in any particular place in the world, this is the same day, again looking at the same set of models, the same 4 variables. In the upper left, the sea surface height, below it sea surface temperature, and to the right, lower right-hand corner, speed being contoured. And if you look at that picture, you see lots of structure on scales, sort of those dominant eddy scales of 100 kilometers or so, that sort of size. And if we go forward or go backward, I can't go backward and forward with that. The keyboard, and the keyboard's here. There we go. I'm going to go, if I switch between this one and that one, you can see that there's some features that are about the same, but you'd have a hard time jumping from one to the other 2 weeks apart. This is a model run daily, and I could put all the frames up, but I didn't, just to show you 2 weeks apart. Now, same sort of thing anywhere in the ocean you can go. Here are the same 4 variables near the Hawaiian Islands. Here's picture number 1, picture number 2. Go back and forth between those. You could recognize one from the other, but there are certainly significant changes. So on timescales of 2 weeks or so, you really start to get substantial changes, and that really makes it a hard ocean to study. How can you study how can you sample a turbulent ocean with finite resources? Well, the key here is that expensive access to the sea is the principal impediment we have in ocean sciences. It always has been. We typically have gone out historically early on in ships. We could average over eddies by spatially making long sections. That's the sort of WOCE approach, with with a relatively few extremely capable platforms, platforms that are really quite mobile, and we call those ships typically. A next approach would be to average in time at a few locations with modestly capable fixed position platforms, that is fixed position platforms, ones that aren't mobile. And those offer persistence, and that's what moorings gave us. And what we really need is one of the things that has been lacking is a way to go from one description to the other, use both of those together, and be able to average in space and time across eddies, resolve eddies, or average over them with a network of relatively simple platforms combining persistence with mobility. Lots of platforms, relatively simple ones that can move around and also stay there. So here's a picture from WOCE of the one-time survey. I may have gotten the dates wrong here. I think it's about 12 years that we had WOCE sections going on to complete this picture. I've seen another estimate of 7 years for the one-time description. But in any case, the total cost was something over $100 million, and the annual cost was something like $10 million. The per profile cost is something like $15,000. So each time you make a CTD, it's about $15,000 if you use this kind of way. So I'm going to shift now suddenly to neutrally buoyant and profiling floats. And here's where I'm sort of a tourist. This is a famous old picture that everybody likes. Why does everybody like it? It's got a cat in it. Okay, there's the ship's cat. This is John Swallow working with one of his floats that he called a float. Everyone else calls it a swallow float. And these were floats that he would launch off this ship, and he could track them acoustically. It was basically a pinger, and he would with a pair of hydrophones on the ship, he could range on this float and tell what its position was. So he had to keep the ship nearby, and basically by doing that, he was able to discover that in fact those slow sorts of circulations that were in Stammel's model didn't exist at all in reality. They were it was really an eddying ocean. He's credited with discovering mesoscale eddies in the ocean. Well, in float development, the next big step was to make something that was trackable not just from a ship, but from some fixed hydrophones. You'd put out some moorings and that would be listening stations and listen for this for big sounds from this giant organ tube of an instrument that was afloat that would go to some neutral density and float around in the ocean for months and months. So that's a big step, to be able to go for a long period of time and remotely figure out where the float goes, and by that figure out what currents are. Well, Doug Webb and Tom Rossby particularly turned this around, went from so-called SOFAR floats to RAFOS floats, that is SOFAR spelled backwards. And there's Tom holding a RAFOS float. This basically turned around the procedure. Instead of the float making the sound, the float here records the arrivals from a number of moored sound sources. So it's the same general idea, but reversed. And Tom has pioneered this, and a lot of people, his students included, have used this technique to try and track motions around the world. And I'm suddenly fast forward to what we see now, or a recent paper. This is from a paper by Amy Bauer and Susan Lozier and co-authors. And in the upper left is one of these piping diagram pictures, and in the lower left is what really happened in the ocean. And what Amy and Susan did was pick a section here on the Labrador Current and launch floats occasionally, periodically, and try and see if they stayed in the western boundary current. The expectation was that they would round the Grand Banks and move on off and form part of the deep western boundary current and off the east coast of North America. And of course, what really happened was they planted all these floats here, and you could see after some period of time, I can't remember how many months they ran before they surfaced, but these floats were all over the place, and only one or two of them actually got in the deep western boundary current and went down along the plumbing of the pipeline. Most of them diffused away. So here we go with a really eddy-rich ocean. There is eddy diffusion that we don't really understand, and we don't really have a way to efficiently observe and understand what the eddy fluxes are, particularly in the ocean's interior. Well, the next step in float technology was another one. This is it was done by Russ Davis together with Doug Webb, and what they exploited was a float that could sit for a long period of time, maybe 10 days, maybe 2 weeks, maybe a month, on a particular at a particular depth, and then periodically pump itself up to the surface using buoyancy to get up to the surface. And then there's an antenna on this float that would signal to Argos and would send back just a little bit of information, basically a location and a temperature profile. And it uses the wonderful data communication rate of about 1/10 of a bit per second, about 1/10 of a baud. Okay? Most of you can't even fathom how slow that is. Back in the day, though, that was fast. That's all we had for open ocean communication. Let's see if I can get this picture up. And now we have the Argo network of profiling floats led by NOAA in the U.S. It's an international program. They've managed to put together, right now, over 3,200 floats are out in the ocean right now. They come up every 10 days. They have global coverage. You can see they're all over the place. They have an average spacing of about 300 kilometers away. And I heard Steve Pitcheritz of NOAA describe this as this is a Washington bureaucrat way of describing it to other Washington bureaucrats. Each float on average occupies an area equivalent to the state of Virginia. Why do you pick Virginia? Because that's where Washington is, right? So that's a way to think of it. So it's not exactly fine coverage, but it does give you a lot to gives you a way to see what the large-scale motions are like in the ocean. So here's a picture of a contrast in the Southern Ocean in particular of how much data there was, how many profiles there were in August from 1951 to 2000, over a 50-year period. That's that top picture of profiles that went deeper than 1,000 meters. And the source is the World Ocean Database. And you can see there are really rather few. This is in August. That means it's wintertime in the southern hemisphere. Not only do ships not like to go there, it's just rough to do it. It's hard to do. And now in just 5 years, and the lower panel, in just 5 years, Argo has all of these places as profiles. Just a huge difference in coverage. And what can we do with this? You can do things like from the WOCE in the upper left, you could order thousands of profiles to put together a picture of, say, dynamic height or potential temperature here at 500 meters. On the right is the same quantity, but averaged with hundreds of thousands of floats. Much more accurate. You can actually say what the average is, say what the standard deviations are, have some idea what the error is. I picked these pictures out of a presentation from that Dean Remick gave me last week, and there are just a few highlights of what WOCE is doing. There's this big Indo-Pacific subsurface circulation. I can't really move the mouse adequately to do it. There's one big gyre, this Indo-Pacific supergyre. We can actually resolve it with, or Argo can actually resolve it with all its resources. Now, another example is looking at the meridional overturning circulation in the North Atlantic. Since a lot of the floats are out of, the currents are out away from the boundaries, since the Argo network doesn't really resolve the western boundary currents, out in the middle it can, and it can resolve things, and you can actually see annual and interannual changes in meridional overturning circulation, and compare that directly to what comes out of the rapid MOCA estimates at 26 north. So this is an estimate of variations over the last 8 years or so in the upper right of northward transport at 41 north at a completely different latitude. And down to the lower half of this slide shows us the warming in the southern hemisphere. There's the Southern Ocean. This is the north end. This is the top 2,000 meters. And this is the difference in temperature between Argo and the World Ocean Atlas. And a red temperature means the newer measurements are warmer. So you can see places of warming and cooling, but really the place that is cool from top to bottom, and if you add it all up in total heat content, the place that has the biggest heat content change is the Southern Ocean. And there's a place that we just didn't really go before we had things like floats. So those are some examples of what you can do with Argo. Well, four-dimensional sampling, AUVs are the things to do that with. They're long-range subset or gliders, and I'm going to concentrate on really long-range AUVs. I'll show you a couple of AUVs, the history of AUVs in 2 slides here. AUVs are relatively fast, hence most of the propulsion energy is against drag. That's what the batteries inside those vehicles are ultimately fighting against. Whereas gliders are deliberately slow, so mismatches in response to their response to pressure and temperature compared to seawater become important things, not just drag. So there's one of the earliest AUV pictures I could find off the web. This is the SPURV vehicle, Special Purpose Underwater Research Vehicle that Terry Ewert and colleagues put together at University of Washington APL. And I was stunned to see that it was in 1957 that they did this. And for obvious reasons, it looks kind of like a torpedo. It's a modified torpedo in effect. And notice that the endurance of this is about 4 hours and went about 2 meters per second. Its range was about 30 kilometers. It's a fairly big, heavy thing, 464 kilograms. Well, fast forward 50 years, and here's the AutoSub 6000 that the UK has. Two different pictures of it. It's obviously a big beast, 2,000 kilograms, really quite a huge thing. The range has increased considerably to 741 kilometers. Its endurance is something like 206 hours, so that means something like a little over a week at a meter per second. Well, remember the mesoscaletes moving around in a week. They haven't really gone very much, haven't gone very far. This sort of range, you could go across a mesoscaleti a few times, 7 times or something like that. It's a little bit frustrating. So let's talk about gliders. Gliders are basically, they're buoyancy-driven AUVs that go very slowly, and I'll come to that in the next slide. But I want to talk about the key enabling technology. Why didn't we have gliders before? Well, one was GPS navigation. That's essential. That didn't come online until the late 80s. I remember going to sea and having the luxury of having GPS for a few hours one day, and the same few hours the next day. That wasn't that long ago that that oceanography was like that. The other thing was low Earth orbit satellite communications. The one that we all use now, or lots of us use, and I can't wait to go to the Iridium booth tomorrow to find out what's new with them. But Motorola put together this thing called Iridium that was a project that put originally 70. They wanted to put 77 satellites up. I think they did it with 66. It was a $7 billion system, and it went bankrupt because the cell phone companies basically outcompeted Iridium for customers. Iridium, as one of my friends said, is a perfect system for places in the world where there are no customers. It's not a great business plan. But it went bankrupt. Some investors bought it in for $25 million, put it back up, and it started the data channel. And we send data at about 200 bytes per second over it. Well, that seems incredibly slow to any techie that you found in the street of San Francisco, almost anyone else in this building. But 200 bytes per second is a factor of 10 to the fifth, 100,000 times faster than Argos. And instead of spending $40 for a kilobyte, which was at one time the price for Argos, you spend less than this coin per kilobyte. What's a kilobyte? Kilobyte's about a page of typed print is maybe 4 kilobytes. So you don't send a lot of love letters to your friends, not to your friends, to your lovers at $40 per kilobyte. But you can actually approach to doing it with Iridium. Lithium batteries. Some time ago, I remember seeing that lithium batteries, they were developed in the 80s, and there's still safety concerns associated with them. They have the highest energy density we can find available for primary lithium batteries are really the best there is still, and their energy density hasn't changed very much in 20 years. We haven't seen other things to come along to replace them, but there's still, say, safety is a concern. There are occasional fires, and particularly on airplanes, people get pretty afraid about that, and there are more and more restrictions. We can't send autonomous vehicles with lithium batteries in them on commercial aircraft in this country. We can only send them on commercial passenger aircraft. We can only send them on cargo-only aircraft, and the rest of the world is probably not far behind making that same decision. It's hard to send these things around, but at least we can do it. The other things that a buoyancy-driven device has to have is a small high-pressure pump. We adapted one from in our community from the downhole seismic industry, and it's a little tiny pump that sits at the end of a drill bit on the end of a long pipe could deal with pump at high pressures, and that's exactly what we need. And then the last thing is a low-power sleep mode processor. You'd be surprised what we use. We use something, typically the typical standard for this in the community is something called the TT8 from Onset. It's basically a little bit more modern than 1960s PCs or 1970s PCs. If there was a PC in 1970, maybe 1980 PCs. Pretty twinky little processor, but it can go to sleep and you can turn it effectively off for a long period of time. And that's how we use most of these vehicles. We actually have them go to sleep and not be on most of the time. The hands aren't on the wheel, except occasionally a clock comes along, the whole system wakes up, makes some measurements, and then goes back to sleep again. Keeping that duty cycle low is essential. So glider energy use, we have fixed energy source, lithium batteries. You can harvest energy from the ocean's tropical circulation if it's available, but certainly at high latitudes it isn't available. There might be a 1,000-meter mixed layer that doesn't give you much thermal contrast. In fact, zero, of course. So there is no thermal contrast to harvest there. So lithium batteries have been a good choice here. The buoyancy engine does work to overcome three things: hydrodynamic drag, the potential energy gradient of thermal circulation, and differential compressibility between a vehicle and seawater. So the first thing to note is that hydrodynamic drag is quadratic in speed. The reason those early AUVs and most propeller-driven AUVs don't last very long is that they go fast. If you go half as fast, the drag is a quarter as much, but so you can stay out 4 times longer going half as fast, so you can go twice as far. You can run that thinking all the way down to zero if you can, but you can't in the ocean. You get down to a speed that's a speed comparable to the ocean currents themselves. So you'd like to be able to go just fast enough to navigate, but not so fast that you use a lot of energy, and that's where gliders have found their niche. The other things that we use energy for are things like sensor operation and processor operation and communications. In something like Sea Glider, those are about 15% of the energy. About 85% is buoyancy work. Well, I made this slide about 5 years ago, and it was a summary of all the tracks that we could find that gliders had made of Slocums, sprays, and Sea Gliders. All the deployments from over about a 2-year period where they were actually working in the ocean. Yeah, I could see if I rocked the projection just right, I could get them all on one side of the globe. Well, that's no longer true. I can't even make a picture like this anymore. These things are all over the place. Lots of people have decided they're pretty interesting. Oh, darn. Went right past my favorite new slide. You've all heard about Prince William's engagement. Well, he got engaged to an autonomous vehicle several months before he got engaged to this woman he's going to marry. Here he is on the deck of the Southern Surveyor in Sydney Harbor talking to Steve Rintoul of CSIRO. And you can see that this is an English reporter. Doesn't that guy look like an English reporter? There's Prince William really being taken by a pink sea glider at his foot. Well, he's not new at this. The Secretary of State engaged with a sea glider while she was a senator. There she is in the Russell Senate office building, admiring one of our sea gliders at a briefing for S&T program managers in 2005. Well, I've mentioned Sea Glider. I'll show you some Sea Glider results here. This is the vehicle that we developed at University of Washington. What you're looking at is a track of Sea Glider number 144 on line P last year and the year before. It started out at Ocean Station P, where that cross is, if I can get the mouse to cooperate. There it is. So it spent about 7 months here doing a pattern, and then started swimming back toward the coast. The reason it swam back toward the coast was the ship wasn't available. The Canadians run a ship that goes out there 3 times a year. They go in June and August and February. And often when they go in February, they can't even do any work. They can barely make a CTD cast. The conditions are so awful at Ocean Station Papa. But a glider doesn't seem to mind. Gliders are really my friends because they don't get seasick. They don't care about, of course, I think it's because they don't have to smell, they don't have the vibration of a ship and don't smell diesel smoke all the time. But maybe that's the key. But they don't really mind the heavy weather at a place like this. What you're looking at is the longest autonomous mission to date by any AUV. It lasted 292 days. It went 5,500 kilometers through the water. That's not drifting over the ground. That's through the water distance. And 5,500 kilometers is a little bit longer than the distance, the Great Circle distance, say, from New York to Lisbon. So it's really quite a long mission. And out at Ocean Station Papa, we did, this is my last attempt at a joke. This is a pattern that we seem to show. This looks like a numerical model, doesn't it? With a grid of places, maybe an OCE that we would be trying to design a program around with little current arrows and so forth. It isn't exactly that. It's a painting by a Spanish artist. It's hanging in a museum in Mallorca. And we did something like it with our gliders. And that's one of our pretty pictures of tying nice bow tie. Well, this is an example of a place that it's pretty easy to run gliders because the currents, the depth average currents, are so low here. We were able to do this for many months. Here's a picture of recovering one of these 9-month missions. We had one 9-month and one 9.5-month mission, as well as a 3-month mission at Ocean Station Papa. Here they are after 9 months pulling this glider out of the water, and there's the amount of fouling that it has. Just a few little barnacles starting to grow, and this is really pretty remarkably little fouling for such a place, for a place that's quite productive. That's in the entrance to the CT, the connectivity cell. Here's another picture that I saw sometime later. This is the worst fouled sea glider I've ever seen, and it was on a mission that was only 11 weeks long in the Southern Ocean with dives mostly to a kilometer depth, except for a few days of order 200 meter deep dives in a warm eddy. And I'm speculating that all this fouling happened from barnacles that were able to get aboard while it was staying near the surface for a long period, for some period of time. It's ultimately the exposure in the photic zone is what really gets you in fouling. If you could stay away from it by staying deep, spending most of the time deep, you're better off. So here's a time series from that Ocean Station Papa record. The top 1,000 meters contouring temperature. This is 18 months across here, and the vertical black lines, the dashed and dotted ones, signify particular targets in that 5-target pattern that we had. So you see places where it looks like there's a periodic structure in time. Here, that's really a periodic structure in space. You're seeing a spatial structure periodically in time. So we're doing space and time at the same time, and you're able to work out, say, seasonally things like the photographs of current shear. This is season by season from summer of 2008 through to autumn 2008, winter 2009, and on through autumn of 2009 through 6 seasons. And you can see very slow changes there. It's really a remarkably slow place to work on, and there isn't a lot of eddy energy there, but we're able to, whatever eddy energy there is, we're able to average over it quite successfully. And I won't go through the calculations, the further calculations from this in the interest of time. I just want to move on to another. I'm going to go through about 6 of these sea glider missions of various kinds. This is a long one. This is 5.5 years off the Washington coast, and where we sent gliders from the edge of the continental shelf out about 240 kilometers to a target. They'd turn and go to a target that was on the shelf farther north, turn around and come back again. Each of these transects took about 2 weeks. Some of them got moved around by eddies, some didn't. Occasionally we got moved into Canadian waters. I haven't been arrested yet for crossing the border into Canada to go skiing. I'm afraid that'll happen someday. We obviously did this without permission, without control. We couldn't control it. But this is an example of something where we made these fortnightly sections for 5.5 years. We had 110 sections, 25,000 kilometers of track over 5.5 years. And the data collection cost is basically something like $15 a kilometer a section and $45 a profile. It's really pretty remarkably cheap. If you think of what it would take to do that with a ship, it would be prohibitive. So here are some of the kinds of signals that we could see. This is 100-meter temperature, and you can see slanted pictures here of warmth happening near the coast, and then later on offshore. Each of these dashed lines marks a year. So you're seeing a westward propagating or an offshore propagating kind of signal. Notice that it also started off with blue colors, sort of colder than the mean, and ended up in blue. And in the middle are a lot of red colors. So there's an interannual change as well. And you can see that in temperature and salinity. These are temperature salinity diagrams. This is the salinity axis, and then the time axis is the other horizontal one, temperature vertically here. And you can see these bow down in the thermocline to being rather bowed up a little bit for a few years and then bowed down again. They're both seasonal and interannual changes here. I'd like to invite you to, I get to do this, I get to invite you to see my student's poster, Noel Pellin's poster outside this afternoon on this to look at more detail. Okay, project number 3. Here's an even a more energetic place. This is the Iceland-Faroe Ridge. We tried to send gliders from Iceland, which in this inset, if I can point to it in the lower left, see if I can find the mouse. I can't seem to find the mouse, so I'll point to it with the green. There's the Faroes, and this is Iceland. This is the Iceland-Faroe Ridge. The Nordic Sea's on this side, cold water. There's that cold water. The Iceland-Faroe front draping up on the Nordic side of the Iceland-Faroe Ridge, and on the south side, the Atlantic waters. And notice that this thermocline comes down and it's draped along the bottom. We almost always see a mixed layer 40, 50 meters deep on that slope, and above it, geostrophically, there's some shear in that thermocline, in the sense to send water along the bottom water along the bottom to the north and west. So part of this is to try and figure out how much water is coming, bottom water comes through the the Fairback Channel and spills out and goes directly downhill versus how much goes out and filters along the, stays along the bank, conserves its F over H and goes for a long ways. I should have pointed out 18,000, almost 18,000 profiles that we made. Not nearly as controlled. We couldn't control the position of the sea glider in the upper left. Instead of making nice straight transects zigging and zagging along the bank, we couldn't do that because of very strong currents, and we basically were able to ferry the gliders over to Iceland and back, and let the eddies move them around, and we ended up with this scattered distribution of points. And in color is bottom temperature. So you can see this very cold water coming through the Fairback Channel and spilling down like that. You can also see wisps of it moving off along the bank and getting warmer and warmer and warmer as mixing of that overlying thermocline mixes into the bottom. You can also see some cold spots that come over directly over the Iceland-Faroe Ridge as well. And an example of the kinds of things you can do with it is to make, from this picture, make synthetic sections, and look at these synthetic sections, and you can see in the Fairback Channel the cold water that's quite dense, and it disappears as you go downstream here, and things get warmer and warmer. So there's some downstream sense in that direction, and we can actually make some estimates of flow with that. So now we're on to the fourth one. This is one that Craig Lee supplied me with. Craig Lee is a colleague at University of Washington, and he has a glider operation that does lots of things. There are some very innovative things. One of these is to work in the Kuroshio with these gliders that are a little too slow to stay in one place in the Kuroshio. They made repeat sections along with Luke Granville and also Dan Rednick at Scripps using spray gliders. Sprays and sea gliders went together along this, making these transects, and did it repeatedly quite successfully. This is an example of a concurrent sea glider and spray section. The arrows here are currents, depth average currents in the top 1,000 meters, and you can see that there's some amount of eddy activity as well as the stream itself. Moving on, the second of these experiments, this is one that Craig and Eric Tesoro, Mary Jane Perry, and Katja Fennel worked on. This is an example where you take two types of autonomous vehicles. You take a float, a neutrally buoyant float, and let it move around in the mixed layer and track it with sea gliders as you go, and come out with a ship periodically and do a process experiment. This was a North Atlantic bloom experiment, and one of the things that these are data from this profiling float. You can see chlorophyll here changing from not very much to quite a lot, and this is where a bloom started, the spring bloom started, and it was stalled out by a storm, and then it started up again. Well, you can only make these, and you can see things like net community production export here. You can see things like the nitrate. Nitrate is on an inverted scale, so red means low nitrate. You can see there's lots of nutrient to begin with, and then it peters out later. And this is the kind of thing that you can do by combining all three techniques of gliders, floats, and ships. And now finally, the third one that Craig gave me is in the Davis Strait, where they have been putting gliders across the Davis Strait to look at freshwater and fluxes through the Davis Strait from the Canadian archipelago into the Atlantic. And there's the track of a glider, and if I'm lucky, this will be a movie that we'll start to show. And there's the ice edge showing up. The glider comes out from underneath the ice, goes back underneath it, comes back out again, wanders around, comes back out, and they head it back down toward Greenland and pick it up. Well, this is that wasn't I'll play it again. It didn't exactly make straight sections. These were, the reason it looped down to the south was it was using acoustic navigation. So instead of making a GPS fix, when it's under ice, it has no choice. It's using Rafos navigation to figure out where to go next. When I started working with sea gliders, I thought they were hard enough. And when Craig and Jason started talking about doing this with acoustic navigation, I thought, wow, this is really going to be hard to do. But they've actually made a lot of progress and are succeeding in doing it. In this particular winter, two winters ago, they were under the ice for 51 days and went about 800 kilometers under the ice and came back out successfully. Right now, Craig is using this same technology he has two floats in the Ross Sea, working with these collaborators. So gliders under the ice is really a possibility and a reality. Here are sections. This is an ice-free and an ice-covered section, and notice this is salinity being colored. This is not as fresh as that is. Notice that it's much fresher when it's ice-free, and when it's ice-covered, of course, the brine rejection is showing you a lot more salty water. So working through sections like that repeatedly over the winter will tell us a lot about flux from freshwater flux from the Arctic. So now finally I have a few minutes left to talk about my favorite latest project, which is gliding into the abyss, the deep glider. Well, as I like to say, it's easy to glide into the abyss. Lots of people have done it. It's gliding back that's hard. And this is our first attempt attempt. This is our first vehicle. It looks a lot like a sea glider. This is supported by O&R. We thought that this was a nice shape. We made a hull out of carbon fiber, and it turns out this is of course a tapered structure, and it has a tapered wall thickness, and it's really at the state of the art a composite construction to make one of these things. It had the unfortunate character that it was much stiffer than seawater, so when you sent it out from the surface and made it heavy and made it dive, it would slow down and slow down and slow down. This is vertical velocity plotted left and right against depth. This is going down to 2,700 meters. Then the glider would pump and start up. It was buoyant, and then it would lose its buoyancy. But what's going on here is that the water around it is compressing more than the stiff hull, so you're gaining buoyancy as you go down. And in fact, if you wanted to descend any further, you'd have to collapse the swim bladder to go even deeper, but then have to spend the energy to pump it back to make it come back. So that turned out to be a large part of the energy budget. The other problem was that we couldn't make these reliably. We asked, this is my next joke, see if you can laugh on this one. We use the composite structures were made by in the Seattle offices of a Chicago company. It's called Boeing. Ta-da! San Francisco audience doesn't get that joke. They must be Airbus people. But we kept having these problems. We would spend something like $40,000 or $50,000 to make one of these parts, and obviously on a research budget that doesn't work out. We collapsed 3 of these things, and we said, hey, we just can't do this anymore. So we revised the design into something that's just a right circular cylinder, and we had flooded nose and tail fairings to put instruments in, and also something that we call a compressee to make up for this compressibility mismatch. And we were also able to reduce the hydrodynamic drag. So here's a robot building a robot. This is in Phantom Works in Seattle at Boeing, making a nice big tube we cut into 3 pieces and made holes out of. And there's one of the holes getting the seal of approval from Jim Ossie, the design engineer. We took these holes to about almost 6,500 decibars before we started to see evidence of buckling of the hull, so we stopped at that point. And it turned out that we thought that the sea glider shape was this nice low drag shape. It turns out that when we made models and used the right Reynolds number, we found that the sea glider actually had about 20% more drag than a shape like this that's a right circular cylinder with an ogive tail and an elliptical cone on the front. So we're obviously using that shape. There's the reason that the sea glider has a certain amount of drag. There's flow separation off the back of it. I want to spend a second on this slide. This is depth, and these are contributions to volume change of different components. Suppose you had a mass of water. If you take that same mass of water at the surface, let's say it's 73 kilograms, and look at its volume at the surface compared to the volume at 6 kilometers depth, it's about 3% smaller at 6 kilometers depth, and most of that's because of compressibility, but some of it's from thermohaline variation as well. If you look at a hull, a relatively stiff hull, it might be only half as compressible as seawater. So there's a big change here of over 1.5% of volume change between those two, and that's what is the compressibility mismatch. That's what makes a vehicle get relatively more buoyant as it falls down into the ocean and the water compresses around it, and it doesn't compress very much. Well, we looked and we found something called that we call a compressee. That's a word coined by Tom Rossby. He had a mechanical compressee for one of his floats. We've actually found a liquid that we can use that has the properties that's about 5 times more compressible than seawater. So a small amount of it added to our hull, if we add these two things together, we can just about compensate for what seawater does. And the net buoyancy is this curve. So we can keep the net buoyancy, we can make it neutrally buoyant to within about 1 part per thousand in over the full range of depth in the main, over 99% of the ocean down to 6 kilometers. By comparison, to provide thrust takes about 0.2% change. So we're basically down at a level that we're just using energy to provide thrust, and we've stopped having to spend it against thermohaline stratification and against this compressibility mismatch. This has big implications for floats as well. We'd passed that picture. Let's see if I can go back. There we are. This is like the picture that I showed you before, but with the compressee, we can have it go down very steadily at one velocity, pump, and it comes back up. It's much more controllable, and we spend a lot less energy. So what are we doing with this? I wanted to test it. If I say I have a 6-kilometer deep instrument, I have to go into water at least that deep. Well, it turns out that the convenient place for us to work is over the Puerto Rico Trench. It's about 8.5 kilometers deep. Why there? Well, for one thing, there's a nice signal here. There's a deep western boundary current to go across. Another is that Puerto Rico is part of U.S. territory, so we don't have to go through customs, and we don't have to ask for permission to work here in those waters. We can also fly here with they have cargo aircraft that go there, so we can ship it and get it, and we basically get a small sport fishing vessel, I'll show you in a second, and go offshore. So we've tried to launch here, and the idea is to occupy part of one of the WOCE sections to where it intersects the 24 North section and come back over and work as part of the rapid MOCA array. Well, we haven't made it over there yet. We've just been fumbling around near San Juan so far, but we will make it. This is the Deepglider going in the water. You can see that just 2 very young men can put it over the side by themselves. And the guy taking the pictures unfortunately missed the picture between here and here. He was seasick. That's why they threw him in the water and gave him a camera. But that's what you get for a non-paid photographer. But that's a Deepglider in the water. And we have been able to make sections short ways off the coast down to 5.5 kilometers depth. We actually haven't gone to 6,000 meters. We've only gone to 5,920 so far. So we'll make it. But this really opens up the possibility of being able to make full ocean depth sections for long periods of time. These are the zigzag patterns of say contours of density, temperature, and salinity offshore there off of Puerto Rico. So the Deepglider capability is that it pencils out that we should be able to keep these out for 18 months. I'll be happy if we can go over a year anywhere, because that means that we can go to some place in good weather and come back a year later in good weather, and we don't have to deal with everything awful in between. Almost every place in the ocean has some nice weather at least one part of the year. The range works out to about 10,000 kilometers. That's the pole to equator distance, with continuous diving to 6 kilometers. So we basically can start doing things like some of those WOCE sections. It measures temperature, salinity, and dissolved oxygen. We may be able to put other payloads in it as well. But we can actually start to work on the eddy problem. So we could address eddies. We could actually measure their fluxes and flux divergences. Those are things that are only done in models now. We don't really have very good ways to do it with other technology. So those eddy fluxes have yet to be definitively observed in situ, and something like Deepglider may be able to make a lot of progress toward doing so. So Argo floats get the basin scale in the upper ocean. Gliders can survey boundary currents and eddies. The main things are that persistence and mobility are crucial, both of those together. So finally, the last word, an autonomous revolution is really underway in the ocean. It's well underway. I look back to, in my career, I'm an old guy now, but I remember going out and using Nansen bottles when I first went to sea And now we basically can measure temperature and salinity and some other things like oxygen and some biological variables, chlorophyll and fluorescence. We can do it completely automatically and have it done far away in remote places and at very low cost. So smart, small, mobile, persistent, inexpensive platforms are crucial to describing our turbulent ocean in the detail that we need to have in order that it may be understood. And I think we're getting there. And if I live so long, it would be interesting to see what the field will look like in another 20 or 30 years to see how much farther these mobile kinds of measuring devices have gone. Thank you very much.
Thank you very much, Charlie, for a wonderful journey through space scales, time scales, pipes, eddies, and for showing us where this field is heading. A lot of exciting possibilities are opening up, and it was really great to see that in one comprehensive review and at the same time outlook. We are out of time for questions, so those of you who want to have further information, please catch up with Charlie here at the front of the room or outside. I would like to thank Charlie again and close the session with a last round of applause.